Welcome, this is MA 259, and this is section 6.1/6.2. This is really part B of that assignment we started uh, already. So what I wanted to point out here was in 6.1, question number 13, and the next several questions, they ask us to solve the system of differential equations and determine if the critical point, 0, 0, is stable, asymptotically stable, or unstable. And so I've actually done that. I'm not going to ask you to do it, but we're going to use the techniques in section 6.2 to actually solve these, answer these same questions. All right, so what I did was copied the system down, and I set them both equal to 0. And sure enough, I get the fact that there's a critical point at xy equals 0, 0. Now, we already told that from the instructions, but I was just sort of verifying that. So then I solved this system of differential equations. So I did wrote it in matrix form here, and so my A matrix, and I did the A minus lambda I equals 0, and I end up with lambda equals minus 2 with a multiplicity of 2. And I apologize, my paper, when I scanned it, looks like I have lots of smudges here. So anyways, when I have A minus lambda I times a V vector equals 0, and I put in -2, I end up with the 0 matrix. And so there are infinitely many choices for my eigenvector that when I multiply by 0, 0, 0, 0, I'm going to get 0, 0. And the only restricted choice I have is the eigenvector being 0, 0, because that's the one case where it can't be restricted. And what I need to find then is 2 linearly independent eigenvectors. So I chose 2 linearly independent eigenvectors to represent here. So I have 1, 0 as one of my eigenvectors, and sure enough, when I put 1, 0 here and multiply it by the 0 matrix, I'll get 0, 0. And V2, which is 0, 1, and I put 0, 1 here, and I multiply it by the 0 matrix, and I get 0, 0. Now, I know that not all of us have taken linear algebra, but as it turns out, this 1, 0, 0, 1, these two eigenvectors form what's called the basis for all of R2 vectors. So these two are linearly independent from each other, and in fact, these are and would be considered the most linearly independent eigenvectors. All the rest of R2 can be formed with these two V1 and V2s. So then I put x1 vector times 1, 0 e to the minus lambda t, -2 in this case, and the x2 vector equals 0, 1 e to the minus 2t. And if I separated that out as x and y, so x, we in the past have sort of written these on top of each other, but x equals c1 e to the minus 2t. So that would be C1 times this one, and since there's a 0 on the bottom, there would be nothing for the other part for over here, and since there's a 0 here, there'd be nothing for the C2 part over here. And we've written these sort of x and y on top of each other's before, but here I'm writing them like this. And then we're talking about what's happening at this point 0, 0. So I plugged in 0 and 0, and then that's my initial condition, x0 and y0 at c1 e to the minus 2 times 0, and same respectively y0 c2 e to the minus 2 times 0. And I end up with xo equals c1 and yo equals c2. So my I suppose you could say my particular solution to this differential equation at the point 0, 0 is this initial condition, x equals x naught e to the 2t, and y of t equals y naught e to the minus 2t. And those are stable things, right? Those are what we would call stable things. Then our book goes on to tell us in the direction what we should do is make a phase plane portrait with some sort of computer and figure out how to classify those nodes as stable, unstable, improper, proper, and all these things. Okay, so what we're going to do though is now skip on to section 6.3, and this is there's a table 6.3.3, and this should be a 3 as well, 6.3.7 from your book, and I have copied that down here. And so this is 6.2.3, so I guess this is wrong. This should be a 2, 6.2.3 and 6.2.7. I have copied those down, and they give us this little chart of eigenvalues of A and the type of critical points. And so we have the case where we have their real numbers, and they're equal, and they're negative. So I look at their real numbers, they are equal, and so there's no part here for negative or positive. But here you have real numbers and equal, and so that's a proper or an improper node. All right, so that's the first part we know, a proper or improper node from the real and equal. And then we're told that lambda 1 equals lambda 2, so lambda 1 equals lambda 2, and they're less than 0, so they're negative. And when I look at my other chart, 6.2.7, I have lambda 1 equals lambda 2, and it's less than 0, so it's negative. I have a stable node or spiral point. So that is a stable node or a spiral point. So lambda 1 equals lambda 2 is less than 0, stable node or spiral point. So this is what's called a stable node or a spiral point. And so that doesn't specifically tell us a lot of information when we look at our solution without looking at the phase plane. But when we look at that chart that we have, we find out some more information. Okay, let's do the same exact thing for number 14. So now I'm not going to actually solve the system. I'm just going to use the next section's techniques, the 6.3 or 6.2, in order to solve these. So I find A, and then I do A minus lambda I. So I have 2 minus lambda, 0, 0 minus 2 minus lambda, and set that equal to, take its determinant and set that equal to 0. And when I do that, I figure out that I have lambda equal to 2 or lambda equal to minus 2. So these are real unequal opposite signs. Real unequal opposite signs. And when I look at the table, real unequal opposite signs, it tells me I have a saddle point. If I look at my other table, I have lambda 1 is less than 0 and lambda 2 is bigger than 0. And that tells me I have an unstable saddle point. So when I look at my other table, I have this situation where lambda 1 is negative and lambda 2 is positive. So I have an unstable saddle point. So when I look at these charts, I can tell some information about what my phase plane is going to look like.